Have you ever gazed up at the sky watching airplanes soar through the air and wondered how do they do that? It seems almost magical, defying the pull of gravity with such grace. The truth, however, lies in a fascinating blend of science and engineering known as aerodynamics. From the Wright brothers' first flight at Kitty Hawk to the giant Airbus A380, our understanding of aerodynamics has allowed us to conquer the skies. It's a story of innovation, a testament to our relentless pursuit of understanding the universe and our place within it. In this exploration, we'll unravel the mysteries of flight, delving into the forces that govern an airplane's journey through the air. We'll explore the principles that allow these metal birds to take to the skies and the control surfaces that make their flight possible. So, fasten your seatbelts and get ready for takeoff as we embark on a journey into the captivating world of flight. To understand how airplanes stay aloft, we must first grasp the four fundamental forces at play: lift, thrust, drag, and gravity. These forces are in a constant dance, each playing a crucial role in an airplane's ability to fly. Lift is the force that opposes gravity, lifting the airplane into the air. Thrust is the force that propels the airplane forward, overcoming drag. Drag is the resistance the airplane encounters from the air it moves through. And gravity, the constant force pulling everything towards the Earth's center, is what the airplane must overcome to stay airborne. The key to flight lies in the delicate balance of these forces. When lift exceeds gravity, the airplane climbs. When thrust exceeds drag, the airplane accelerates. Understanding this interplay of forces is fundamental to comprehending the science of flight.
Lift, the force that allows airplanes to defy gravity, is generated primarily by the wings. But how do these seemingly simple structures produce such a powerful force? The answer lies in their ingenious design and a fundamental principle of fluid dynamics. Airplane wings are not flat. They have a carefully crafted curved shape, known as an airfoil. This airfoil shape is crucial for generating lift. As the airplane moves forward, air flows over both the upper and lower surfaces of the wings. The curved upper surface of the wing forces the air to travel a longer distance than the air flowing under the wing. This difference in distance creates a difference in air pressure. According to Bernoulli's principle, faster-moving air creates lower pressure, and slower-moving air creates higher pressure. Bernoulli's principle is a cornerstone of aerodynamics, explaining how the difference in airspeed over the wing's surfaces translates into lift. This principle states that as the speed of a fluid like air increases, its pressure decreases and vice versa. Because the air flowing over the top of the wing travels faster and covers a longer distance, it creates an area of low pressure. Conversely, the slower-moving air beneath the wing creates an area of high pressure. This pressure difference generates an upward force on the wing, lift. The greater the speed difference between the air flowing above and below the wing, the greater the pressure difference, and consequently, the greater the lift generated. This is why airplanes need to achieve a certain speed to take off. As the airplane accelerates down the runway, the lift force increases until it exceeds the force of gravity, allowing the airplane to become airborne.
Section 5. Thrust, powering through the air. While lift gets an airplane off the ground, thrust is the force that propels it forward, enabling it to move through the air and maintain its speed. This forward force is typically generated by engines. In most modern airplanes, jet engines or propellers provide thrust. Jet engines work by sucking in air, compressing it, mixing it with fuel, and igniting the mixture. This combustion process creates a powerful jet of hot gases expelled out the back of the engine, propelling the airplane forward. Propellers, on the other hand, generate thrust by acting like rotating wings. Their angled blades bite into the air and pull the airplane forward as they spin. Whether it's the roar of a jet engine or the whir of a propeller, thrust is what allows an airplane to overcome drag and maintain the speed necessary for lift generation.
Section 6. Drag, the resistance of air. As an airplane moves through the air, it encounters resistance, a force called drag. Drag acts in the opposite direction of thrust, trying to slow the airplane down. It's like the friction an object experiences when moving through water. The shape and surface of the airplane significantly influence drag. Streamlined designs with smooth curves and minimal protrusions help reduce drag by allowing air to flow more easily over the airplane's surface. Engineers spend countless hours optimizing aircraft designs to minimize drag, making them more aerodynamic and fuel efficient. Reducing drag is crucial for achieving better fuel economy and increasing an airplane's range and speed.
Section 7. Gravity, the constant pull. Gravity, the force that pulls everything towards the Earth's center, is the constant adversary of flight. It's the force that airplanes must overcome to stay airborne. The heavier the airplane, the greater the force of gravity acting on it. This is why different airplane designs have different weight limits. Exceeding these limits can have serious consequences, as the lift generated may not be sufficient to counteract the increased gravitational pull. Pilots and aircraft designers must always consider the weight of the airplane, passengers, cargo, and fuel when calculating takeoff speeds, flight paths, and landing procedures. Every aspect of flight must take into account the relentless force of gravity.
Section 8. Controlling the skies, rudders, ailerons, and elevators. While lift, thrust, drag, and gravity are the fundamental forces of flight, controlling an airplane's movement through the air requires additional mechanisms. This is where control surfaces come into play. 3 primary control surfaces, rudder, ailerons, and elevators, allow pilots to steer the airplane, control its altitude, and maintain stability during flight. These surfaces work by altering the airflow over different parts of the airplane, generating forces that rotate the airplane along its 3 axes: yaw, roll, and pitch. The rudder, located on the vertical stabilizer, tail fin, controls yaw, the airplane's left-to-right movement on a vertical axis. The ailerons, located on the trailing edges of the wings, control roll, the airplane's rotation around its longitudinal axis. The elevators, located on the horizontal stabilizer tailplane, control pitch, the airplane's up and down movement on a lateral axis.
Section 9. Aviation's environmental impact. While aviation has revolutionized travel and connected the world, it also has an impact on the environment. Airplanes burn fuel, releasing greenhouse gases into the atmosphere, contributing to climate change. Noise pollution from aircraft engines is another concern, especially near airports. The aviation industry is acutely aware of these environmental challenges and is actively pursuing solutions to mitigate its impact. Airlines are investing in more fuel-efficient aircraft, optimizing flight routes, and exploring the use of sustainable aviation fuels. Researchers and engineers are continuously working on innovative technologies to make aviation more environmentally friendly. From designing lighter aircraft materials to developing electric and hybrid electric propulsion systems, the future of flight is moving towards greater sustainability.
Section 10. Shaping the future of flight. The quest for innovation in aviation continues. From supersonic aircraft that can travel faster than the speed of sound, to electric planes that promise quieter and cleaner skies, the future of flight is full of exciting possibilities. Advancements in materials science are leading to the development of lighter and stronger aircraft, improving fuel efficiency and reducing emissions. Artificial intelligence and automation are playing an increasingly important role in flight operations, enhancing safety and efficiency. The dream of personal air travel is also closer than ever, with companies developing electric vertical takeoff and landing (eVTOL) aircraft that could revolutionize urban mobility. The future of flight is bright, driven by our relentless pursuit of innovation and our desire to explore the skies above.
Section 11. Conclusion. A symphony of science and engineering. The next time you watch an airplane soar through the sky, take a moment to appreciate the intricate interplay of forces and the marvels of engineering that make it all possible. From the carefully sculpted shape of the wings to the powerful engines that propel it forward, every aspect of an airplane's design is a testament to our understanding of aerodynamics. Flight is a delicate balance, a symphony of science and engineering. It's a reminder that even seemingly impossible feats can be achieved when we combine our curiosity with our ingenuity. As we continue to push the boundaries of aviation, we can look forward to even more groundbreaking innovations that will shape the future of flight.